This is Naveen, but now further explain part B of internal logic. Question is basically outline how to compute dissimilarity in student features of and described by nominal attributes, asymmetric binary attributes, numeric attributes in terms of nominal attributes. Nominal values are categories without order, department is or M. Common approaches are simple math, binary similar. For two profiles P and P for a nominal attribute S of P comma P is equal to 1 or 0. If same category, the similarity D is equal to 1 minus F for multi-attribute nominal vector. Average the mismatch is one hot encoding plus numeric distance. Convert each category to a binary vector 1 hot. Then use, for example, cosine or Euclidean on the binary vector. These allow mixing with other attributes as to text. Overlap tool creating coefficient for multi-valued nominal attribute. When attribute may have multiple choices, use overlap jacket. J of A, comma B is equals to A intersection B by A union B. This similarity is equal to 1. Asymmetric binary. Asymmetric binary means 1. Presents is more informative than 0 itself. Example, attended workshop, yes or no, where yes matters, no. Common matrix, Jacquard coefficient. Ignore 0, 0, 1. For two binary vectors, C, C. J of P, Q is equals to M11 by M01 plus M10 plus M11, where M11 is the number of attributes with the 1, M10 is attribute where P is equal to 1 and Q is equal to 2. M01 is where P is equal to 2. The similarity. Numeric attributes, CGP attendance percentage. Numeric attributes support many classical distances, Euclidean distance. Euclidean distance g of e, x comma y is equal to under root of summation of I of xi minus yi per whole square. Manhattan L1 distance. V1 of x comma y is summation of mod of xi minus yx. Shape and distance, maximum absolute coordinate distance, standardization scaling. Before computing this kind of standardized Z score for scale 0, 1. Otherwise, attributes with larger range will dominate. Zeta is equal to xi minus 2 sigma. Maneuver loop distance. Mahala Lubis distance. Dm of x comma y is equal to under root of x minus 1 to the power t s to the power minus 1 x minus 1. Term frequency vector. Keyword in open text field. Text is typically represented as vectors. Term frequency TF created by DF of common similarity, cosine similarity. Measure angle ignores document length. Cos theta is equals to mod of x, absolute mod of x, mod of y upon divided by x dot y. Similarity can be 1 minus cos. Euclidean on TF IDF normalized vector. Compute TF IDF the normalized Euclidean distance between normalized TF-IDF vector relate to cosine. KL divergence Jensen Shannon. Treat normalized TF as probability distribution. Soft summation. Word embeddings for semantic similarity use average word vectors of sentence embedding and their cosine. Now we are moving for next question. Suppose two students faculty interaction profiles are represented as tuples 22, 1, 42, 10 and Q is 20, 0, 36, 8. Attribute represents its R, mentoring, project reviews, attended, assignment, submitted, and constructive is false. Complete. Euclidean distance, Manhattan distance, Minkowski distance, and supreme. Step 1 is compute coordinated wise difference. L is equal to T minus Q. 22, 21 to 0, 42 to 36, 10 to 10 minus 8. 2166. Let the absolute difference del 2162. Euclidean distance is under root of root square plus 1 square plus 6 square with 2 square which is root 45 and root 45 is function 08. Manhattan distance is directly adding these values individually got here. 2162. So this is 11. Minkowski distance is to the power of h and here h is 3. So d3 is equal to 2q plus 1q plus 6q plus 2q to the power 1 by 3 is equal to 8 plus 1 plus 2 1 6 plus 8 to the power 1 by 3 which is 233 to the power 1 by 3 which is equivalent to 6.15. Supremum Chebyshev distance d infinity is equal to max of mod 2 mod 1 mod 6 mod 2. So here as we can see mod maximum is 6 So now let's move for next question. Question number 7. The median score is often a key holistic indicator when dealing with massive student feedback data sets. Proposed methods for median approximation analyze their complexity and suggest heuristics to balance accuracy versus efficiency. Exact methods will feasible. Deterministic linear time selection, medians of median scores. We go of n time, we go of one express speed. Good when you need exact median and can read data multiple times for a random access. Sort and pick median. Big O of n log n time, big O of n of memory or external sorting for disk, not ideal for massive streaming data. Streaming or large scale approximate algorithm. Two heaps, running heap, maintains a max heap for lower half and a min heap for upper half. Each new element inserted big O of n log n time, median retrieved in big O of 1. Memory big O of n, you keep all the elements, but if streaming and you must keep n, memory grows. Practical for online median if you can store data. Reservoir sampling plus exact median on sample. Keep sample of size k. Example k equals 10 to the power 4. Time is big O of n to sample big O of k log k to sort example. Error can be bounded probabilistically with large n of k. You can get time confidence interval. Huge heuristic when you can tolerate probabilistic error. Third is approximate quantile algorithm, guaranteed error. Greenwald algorithm deterministic provides epsilon approximate quantiles with space, stream friendly, mergeable, Q digest, T digest, practical mergeable, T digest is excellent for extreme quantiles and distribution, small memory and good accuracy convenience. Complexity. Update cost typically for amortized constant memory. We go for 1 by epsilon. Histogram binning approach. Maintain fixed bins, approximate median by walking cumulative counts. Space is equals to number of bins V. Accuracy depends on bin width. Fast update we go 1. Good for what? Distribution map reduced approach. Compute local summarizes quantile sketches on partitions and merge. Merge GK and T digest are preferred. Complexity linear total work across nodes. Low network growth. Accuracy versus efficiency heuristics. If you need exact median rarely in data sets at disk, use selection. For streaming or online dashboards, use T-Digest or GK. For small memory mergeable guaranteed error bounded. For simple engineering trade-off, reservoir sampling, which is cheap plus exact median on sample each probabilistic guaranteed. Sample size shouldn't be a desired confidence interval. For skewed distributions or extreme quantile, T-Digest perform better than histogram or GK vector. Many groups maintain separate digest streams per group. Memory skills with hashtag groups consider hierarchical summary. Now, question 8. Given the sample data set, from the sheets we interpret each student as 2D vector. As the table we can see here. Tasks are rank existing students with the profile with similarity to existing Euclidean Manhattan Supreme, normalize each student's vector to unit length and recompute each Euclidean. Here we can see the formula of Euclidean Manhattan supremum cosine normalization of vector. We compute each quantity for h1 dot h5 versus x is equal to 0.1.4 1.6. So differences for each student we can see here s1 is 0.1.1, s2 we get 0.6.3, s3 gets similarly with subtraction 0.2 and this is the other data. By applying Euclidean distance S1, S2, S3, S4, S5, we get these data 0.141, 0.670, 0.282 and 0.22. S5 is 0.608. Euclidean ranking, we get S1, then S4, then S3, then S5, then S. Sum of absolute coordinated distance. S1 is 0.2, S2 is 0.9, S3 is 0.4, S4 is 0.3 and S5 is 0.7. Manhattan ranking is closest to farthest. So S1, then S4, then S3, then S5, then S2. Supremum, Chebyshev, D infinity. So here we get a maximum of both the coordinates 0.6, like here 0.6, 0.3, we get 0.6, which is the maximum of both the fields. Similarly, we get all the data. Now, supremum ranking will be from S1 times S3, then S4 times S5, and S2 is separated 0.6. Cosine similarity. First compute norms. A mod of x is equals to this formula under root of 1.4 square plus 1.6 square. So we get here 2.12. Similarly, we get S1 is 2.26. Now S1 dot 1.5 plus 1.6 dot 1.7. So by calculation, we get 4.82. So now norms we get 2.266 by applying this. Cosine is 4.82 by 2.12 into 2.266. We get approximate 0.99991. S2 is similarly applying by this formula like this 0.99552. S3 dot we get value 5.12. S3 of cosine we get 0.99969. S4 similarly for S5. So the closest ranking higher is equals to more similar. S1 then S3 then S4 then S2 then S5. Normalize each student's vector to unit 10 and decompose the Euclidean distance. Step 1. Normalize feature. Mod of x is equals to 2.12. Similarly, step 2. Normalize each of x and score I. So we get the following values like this. Euclidean distance between normalized vectors and x norm. Compute d is equals to si of norm minus x norm. So by applying this on all these, we get ranking after normalizing with S1.00415 S3, which is this value, and then S4, then S4 is 5.